Welcome to this in-depth course on heat transfer, with a special focus on the design and analysis of heat exchangers. Understanding heat transfer is fundamental to numerous engineering disciplines, from power generation and HVAC systems to chemical processes and aerospace. In this video, we have two primary objectives. First, you will learn to identify and describe the three primary modes of heat transfer: conduction, convection, and radiation. We'll explore the underlying principles and mathematical foundations of each. Second, we will apply these principles to solve practical problems involving heat transfer through composite walls. This will give us a strong foundation for understanding the resistance networks in heat exchangers. By the end of this session, you will be able to confidently explain and calculate heat transfer for these foundational scenarios. Let's begin with the first mode of heat transfer: conduction. Conduction is the transfer of thermal energy between particles that are in direct contact. It happens in solids, liquids, and gases, but it's most significant in solids due to their rigid structure. At the microscopic level, particles with more kinetic energy, which is what temperature represents, transfer that energy to adjacent, less energetic particles through vibrations and collisions. Imagine a metal rod being heated at one end. The heated particles vibrate more intensely and bump into their neighbors, passing on that kinetic energy, and the heat travels down the rod. The rate of conduction is governed by Fourier's law of heat conduction. This law states that the rate of heat flow, Q, is proportional to the negative temperature gradient and the area normal to that gradient. Let's break this down. Q is the heat transfer rate in watts. The term dT over dx is the temperature gradient, or how much the temperature changes with position. The negative sign ensures that heat always flows from a higher temperature to a lower temperature. A is the area through which heat is flowing in square meters. And finally, K is the thermal conductivity of the material, measured in watts per meter per Celsius. Thermal conductivity is a material property that quantifies its ability to conduct heat. For example, metals have very high thermal conductivity, while insulators like foam or wood have very low thermal conductivity. So, to recap conduction, it's heat transfer through direct contact, governed by Fourier's law, and is dependent on a material's ability to conduct heat, its thermal conductivity. Next, let's explore convection. Convection is the transfer of heat between a surface and a moving fluid, which can be a liquid or a gas. Unlike conduction, convection involves the bulk motion of the fluid. Think of boiling water. The water at the bottom gets hot, becomes less dense, and rises. Cooler, denser water sinks to take its place, gets heated, and rises. This continuous circulation transfers heat throughout the pot. There are two main types of convection. First, we have natural or free convection. This occurs due to natural density differences in the fluid caused by temperature variations. The hot water rising in a pot is an example of natural convection. Second, we have forced convection. This is when the fluid is forced to flow over a surface by external means, such as a fan, pump, or the wind. A computer's cooling fan is a common example of forced convection. The rate of convective heat transfer is described by Newton's law of cooling. This law states that the rate of heat flow, Q, is proportional to the difference in temperature between the surface, T sub S, and the fluid, T sub infinity. Here, H is the convective heat transfer coefficient. Unlike the thermal conductivity K, H is not a material property. It's a complex variable that depends on many factors, including fluid properties, fluid velocity, surface geometry, and the type of flow. A is again the surface area in square meters, and T sub S minus T sub infinity is the temperature difference driving the heat transfer. So, to recap, convection is heat transfer by fluid motion, which can be natural or forced, and its rate is determined by Newton's law of cooling, a temperature difference, and a convective heat transfer coefficient that is flow-dependent. Our final mode of heat transfer is radiation. Radiation is the transfer of energy through electromagnetic waves. Unlike conduction and convection, radiation does not require a medium to transfer heat. It can even occur in a perfect vacuum, which is why we feel the warmth of the sun here on Earth. All objects with a temperature above absolute zero emit thermal radiation. The amount and type of radiation depend on the object's temperature and surface characteristics. A theoretical perfect emitter and absorber of radiation is called a blackbody. It emits the maximum possible radiation for a given temperature and absorbs all radiation incident upon it. The rate of radiation from a blackbody is described by the Stefan Boltzmann law. This law states that the radiative heat transfer rate is proportional to the object's surface area and to the fourth power of its absolute temperature. Here, sigma is the Stefan Boltzmann constant, a physical constant with a value of 5.67 times 10 to the power of -8 watts per square meter per Kelvin to the fourth. T is the absolute temperature in Kelvin. Real-world objects are not perfect blackbodies. They emit less radiation than a blackbody at the same temperature. To account for this, we introduce a property called emissivity. Emissivity, represented by the Greek letter epsilon, is a dimensionless value between 0 and 1. It represents the fraction of radiation emitted by a real surface compared to a blackbody. For a real surface, the radiative heat transfer rate is simply its emissivity times the blackbody radiation rate, or epsilon times sigma times A times T to the fourth. And finally, when two surfaces at different temperatures are radiating heat to each other, the net heat transfer is the difference between what each emits and absorbs. For radiation between two large parallel plates, this is given by Q equals the area times sigma times the temperature difference to the fourth, divided by the sum of 1 over epsilon 1 and 1 over epsilon 2 minus 1. So, to recap, radiation is energy transfer via electromagnetic waves, doesn't need a medium, and its rate is strongly dependent on temperature to the fourth power and a surface's emissivity. Now that we've covered the three modes of heat transfer, let's see how they work together in a common engineering scenario. The composite wall. Understanding how to analyze a composite wall is a crucial step before we can tackle the more complex heat exchangers. A composite wall is a wall made up of multiple layers, each with a different material and thus a different thermal conductivity. A common house wall with plaster, insulation, and siding is a perfect example. Heat will be transferred through this wall by convection on both sides and by conduction through each of the solid layers in between. We can model this entire process using an electrical analogy. Think of temperature as voltage and heat transfer rate as current. The resistance to heat flow is called thermal resistance. Let's define the thermal resistances for each mode of heat transfer we've discussed. For convection, the resistance is 1 over the product of the heat transfer coefficient H and the surface area A. For conduction through a flat wall, the resistance is the thickness L divided by the thermal conductivity K and the area A. Now for our composite wall, the heat must flow sequentially through each resistance. This means the resistances are in series. Just like in an electrical circuit with series resistors, the total thermal resistance is simply the sum of all individual resistances. So, for our wall with one convective layer on each side and two solid layers in the middle, the total resistance is 1 over H1A plus L1 over K1A plus L2 over K2A plus 1 over H2A. Once we have the total resistance, we can calculate the overall heat transfer rate, Q. Using our electrical analogy, Q equals the total temperature difference divided by the total resistance. If T infinity 1 is the hot fluid temperature and T infinity 2 is the cold fluid temperature, the total heat flow is simply the temperature difference between the two fluids divided by the total thermal resistance of the wall. This concept of thermal resistance networks, especially those in series, is a fundamental building block for understanding heat exchangers. Let's work through a practical example to solidify our understanding of composite walls. Imagine a cold storage wall, a common application where we want to keep heat from the environment out of a refrigerated space. We have a concrete wall with a thickness of 20 centimeters, on the outside of which is a 5 centimeter thick layer of insulation. The ambient air outside is 25 degrees Celsius, with a convective heat transfer coefficient of 8. The air inside the cold storage is kept at -15 degrees Celsius, with a heat transfer coefficient of 15. Our goal is to find the steady-state heat transfer rate per unit area, represented by Q prime. First, let's draw our thermal circuit. Heat flows from the outside air through an outer convection resistance, then through the concrete conduction resistance, then the insulation conduction resistance, and finally through an inner convection resistance to the cold air inside. This forms a perfect series circuit. Since we're looking for the heat transfer rate per unit area, it's convenient to work with thermal resistance per unit area, which simplifies the calculations. Let's call the total thermal resistance per unit area R prime total. We can get this by summing the resistances, each divided by the area A. Now, let's plug in our values. Remember to convert centimeters to meters. R prime total equals 1 over 8 plus 0.20 over 0.8 plus 0.05 over 0.04 plus 1 over C15. Calculating these values gives us 0.125 for the outside convection, 0.2 for the concrete, 125 for the insulation, and 0.667 for the inside convection. Summing them all up, the total thermal resistance per unit area is 1.6917 meters squared Celsius per watt. Finally, we can calculate the heat transfer rate per unit area. The heat transfer rate Q prime equals the total temperature difference, T infinity outside minus T infinity inside, divided by the total resistance. That's 25 minus negative 15, divided by 1.6917. This gives us 40 divided by 1.6917, which equals approximately 23.63 watts per square meter. This is the amount of heat energy that must be removed per second from every square meter of the cold storage wall to maintain the desired temperature. This example clearly shows how to set up and solve a multi-mode heat transfer problem using the powerful thermal resistance network method. We've now completed our foundation on the modes of heat transfer and composite walls. Let's recap what we've learned. We have successfully achieved our learning objectives for this section. We have identified the 3 modes of heat transfer: conduction, convection, and radiation, and described the physical mechanisms and governing laws for each. And we have applied these concepts to solve a practical problem involving a composite wall, which served as an excellent introduction to thermal resistance networks. This understanding of series thermal resistances is the key to our next major topic, the analysis of heat exchangers, which we will begin in the next scene. Welcome to the next part of our course, where we dive deep into heat exchangers. Today, our main objective is to understand the fundamental concepts and types of heat exchangers, and to learn how to calculate one of their most important parameters, the overall heat transfer coefficient. A heat exchanger is a device that efficiently transfers heat between 2 or more fluids at different temperatures, often without them coming into direct contact. You're surrounded by heat exchangers every day. Your car's radiator cools the engine. The coils in your refrigerator transfer heat from the inside to the outside air. Furnaces and air conditioners rely on them to heat and cool your homes. Let's begin by classifying them based on the flow arrangement. The 2 primary flow arrangements are parallel flow and counterflow. In a parallel flow heat exchanger, both the hot and cold fluids enter at the same end, flow in the same direction, and exit at the other end. In a counterflow heat exchanger, the fluids enter at opposite ends and flow in opposite directions. As we'll see later, the counterflow arrangement is generally more efficient and is preferred in many applications. Now, let's consider the construction types. One of the most common is the shell-and-tube heat exchanger. As its name suggests, it consists of a bundle of tubes inside a large shell. One fluid flows through the tubes, while the other fluid flows around the tubes through the shell. Baffles are often used to direct the shell side fluid and increase the heat transfer. Another common type is the plate heat exchanger. This design uses a series of thin, corrugated plates to create flow passages. The fluids flow in alternating channels, allowing for very efficient heat transfer in a compact space. A key concept for understanding heat exchanger performance is the overall heat transfer coefficient, denoted by the letter U. You can think of U as a single combined measure of the thermal resistance offered by the heat exchanger from one fluid to the other. It accounts for conduction through the wall and convection on both sides. Let's derive it for a simple flat wall separating 2 fluids. We already did this with our thermal circuit for a composite wall. The total thermal resistance is the sum of the inner convection resistance, the wall conduction resistance, and the outer convection resistance. For a flat wall of thickness L and thermal conductivity K, this is 1 over high times A plus L over chi times A plus 1 over ho times A. Now, we define the overall heat transfer coefficient U by the equation U equals 1 over the total thermal resistance times the area A. In other words, U is 1 divided by the sum of 1 over high plus L over K plus 1 over ho. This formula gives us the overall heat transfer coefficient U. Its units are watts per square meter per degree Celsius, the same as a convection coefficient. This value U is incredibly useful because it allows us to calculate the total heat transfer rate in a heat exchanger with a very simple formula. The total heat transfer rate Q equals U times A times the overall temperature difference between the hot and cold fluids, T hot minus T cold. This is the most fundamental equation in heat exchanger design. It links the performance, Q, to the design, A, and the material properties and flow conditions, U. So, the overall heat transfer coefficient, U, consolidates all the resistances to heat flow into a single convenient parameter, allowing for a simplified calculation of heat exchanger performance. Now, let's address a very important practical consideration in heat exchangers. Fouling. Fouling refers to the accumulation of unwanted materials on the heat transfer surfaces. This could be anything from rust, scale from hard water, sediment, or even biological growth. When these deposits build up, they create an additional layer of material that acts as a thermal insulator. This increases the overall thermal resistance between the fluids. As a direct consequence, fouling reduces the overall heat transfer coefficient and severely diminishes the heat exchanger's performance. It also increases pressure drop and makes cleaning more difficult. In design, we account for this effect using the concept of a fouling factor, or fouling resistance, denoted as R sub F. The fouling factor represents the thermal resistance of the deposited layer. Its value is determined experimentally and can be found in design handbooks for various fluids and operating conditions. To calculate the new overall heat transfer coefficient, which we'll call U sub F for fouled, we simply add the fouling resistances to our overall thermal resistance equation. If we have fouling on both the inside and outside of the tube, the fouled overall coefficient U sub F is found from the equation 1 over U sub F equals 1 over U clean plus Rho F plus Rho F. So the fouled resistance is simply the sum of the clean resistance and the two fouling resistances. By using U sub F in our Q equals UA delta T equation, we can calculate the heat transfer rate for a fouled heat exchanger. This is crucial for designing a heat exchanger that will perform acceptably over its entire service life, even as fouling builds up. Let's work through an example to calculate the overall heat transfer coefficient, with and without fouling. Consider a counterflow heat exchanger where hot oil flows through a tube made of brass. The tube has an outer diameter of 2 centimeters and an inner diameter of 1.8 centimeters. Hot oil inside gives a convection coefficient of 200. And cold water outside gives a convection coefficient of 500. Let's also assume fouling factors of 0.001 for the inside and 0.002 for the outside. We'll calculate the clean and fouled overall heat transfer coefficients, both based on the outer surface area A sub O. Because the area for heat transfer is not constant, it's larger on the outside than the inside, we must decide on a reference area. Using the outer area A sub O is a common practice. For a cylindrical tube, the conduction resistance formula changes to this logarithmic term. If we divide the entire equation by A sub O and substitute A equals 2PRL, we get 1 over U sub clean equals the ratio of outer radius to inner radius times 1 over H sub I plus R sub O over K times the natural log of R sub O over R sub I plus 1 over H sub O. Let's calculate the term R sub O over R sub I, which is the ratio of 1 to 0.9. This gives us approximately 1.1y1. Now, plugging in our values for the clean case, 1 over U clean is 1.1111 over 200, plus 0.01 over 110 times the natural log of 1.111, plus 1 over 500. This gives us 0.055, plus 0.000085 plus 0.002. Summing these, 1 over U clean is 0.075585. Taking the reciprocal, we get U clean equals 132.3. WBBM2 K. Now for the fouled case. We just add the fouling factors adjusted to the outer area. 1 over U fouled equals our clean result, plus the outer area over the inner area times the inner fouling factor, plus the outer fouling factor. Plugging in the numbers, we get 0.07555 plus 1.111 squared times 0.0001 plus 0.002. This is 0.00755 plus 0.01823 plus 0.0002, which sums to 0.0078815. Taking the reciprocal gives U fouled equals 126.9 Wm2K. As you can see, fouling has decreased the overall heat transfer coefficient from 132.3 to 126.9. This 4% reduction, if not accounted for in the design, can lead to a significant drop in performance over the exchanger's lifetime. In the previous sections, we saw how the overall heat transfer coefficient, U, is calculated by considering the individual thermal resistances in series. This concept of a series resistance network is the most common model, but it's important to understand that thermal resistances can also be in parallel or in a combined series parallel arrangement. In a parallel thermal resistance network, heat can take multiple paths to flow from a high temperature to a low temperature. Think of this like a fork in a road for heat. A perfect example of this is a wall that contains windows or doors. Heat can flow through the main wall material, or it can flow through the window, which usually has a very different thermal resistance. Heat will travel from T1 to T2, with some of it going through resistance R1 and the rest going through R2. In this case, we cannot simply add the resistances. Instead, we must use an equation similar to the one for parallel electrical resistors to find the equivalent resistance. The equivalent thermal resistance is found by taking the reciprocal of the sum of the reciprocals of the individual resistances. So 1 over R equivalent equals 1 over R1 plus 1 over R2. Solving for our equivalent, we get that it is equal to the product of the individual resistances divided by their sum. Once you have this equivalent resistance, you can use the familiar formula Q equals delta T over R equivalent to find the total heat transfer rate. Often heat transfer problems will involve a combination of series and parallel resistances. Let's say we have a wall made of two materials in parallel, but with a convective resistance on the outside in series with the entire parallel section. The heat first encounters R1 in series. Then it splits into R2 and R3 in parallel. Finally, it flows through R4 in series. To solve this, we work from the inside out. First, we find the equivalent resistance for the parallel section, R23. Then we can treat the circuit as three series resistances, R1, R23, and R4. The total equivalent resistance for the entire system is the sum of these three. So, while series resistance is the workhorse for heat exchangers, understanding parallel and combined networks is essential for solving heat transfer problems in more complex, realistic geometries. We've established the overall heat transfer coefficient U as a key parameter. But how do we determine the individual convection coefficients, H, that go into calculating U? Finding H for a given flow situation is often the most challenging part of a heat transfer problem. It's not a simple material property. It depends on the fluid properties, geometry, and most importantly, the fluid flow regime. Let's first understand flow regimes. They are typically categorized into two types. Laminar flow is smooth and orderly. Imagine water flowing slowly and parallel through a pipe. Turbulent flow is chaotic and irregular. Imagine turning the faucet on full blast. The water swirls and mixes erratically. Turbulent flow is generally preferred in heat exchangers because the mixing of fluid parcels across the flow stream greatly enhances heat transfer. The transition between these regimes is governed by a dimensionless number called the Reynolds number. The Reynolds number, Re, is the ratio of inertial forces to viscous forces in a fluid flow. For flow inside a pipe, the critical Reynolds number for the onset of turbulence is about 2300. Flows below this are considered laminar, and above it, they become turbulent. To calculate the convection coefficient H for turbulent flow in a pipe, one of the most widely used methods is using a heat transfer correlation. Correlations are empirical formulas derived from experimental data. They are very accurate within the range of data from which they were developed. A common and relatively simple correlation for turbulent flow in a pipe is the Dittus-Boelter equation. The Dittus-Boelter equation relates the Nusselt number, another dimensionless group containing H, to the Reynolds number, the Prandtl number, and an exponent Nn. The exponent N is 0.4 for heating the fluid and 0.3 for cooling the fluid. The Prandtl number, Pr, is another dimensionless group that relates the fluid's momentum diffusivity to its thermal diffusivity. Once you've calculated the Reynolds and Prandtl numbers using fluid properties, you can plug them into Dittus-Boelter to find the Nusselt number. Then you can solve for the convection coefficient H since nu equals Hd over K. This process allows engineers to accurately predict the convection coefficient H, and in turn, the overall heat transfer coefficient U, which is essential for designing effective heat exchangers. We've focused on calculating the overall heat transfer coefficient, U, which quantifies the heat exchanger's ability to transfer heat. Now let's turn to how we determine the actual heat transfer rate, Q, in a working heat exchanger. Calculating Q in a heat exchanger is more complicated than in our composite wall example because the temperatures of both fluids change along the length of the exchanger. This means that the temperature difference that drives the heat transfer, delta T, is not constant. It varies with position inside the heat exchanger. To solve this, we define a special type of average temperature difference that allows us to use our simple equation, Q equals UA delta T, where delta T is this new average. This special average is called the log mean temperature difference, or LMTD. The formula for the LMTD is delta T sub LM equals the difference between delta T1 and delta T2, divided by the natural logarithm of delta T1 over delta T2. But what are delta T1 and delta T2? They represent the temperature differences between the hot and cold fluids at the two ends of the heat exchanger. The exact definition depends on whether the flow is parallel or counterflow. For a counterflow heat exchanger, delta T1 is the difference between the hot fluid's inlet temperature and the cold fluid's outlet temperature. Delta T2 is the hot fluid's outlet temperature minus the cold fluid's inlet temperature. For parallel flow, both delta T1 and delta T2 are the differences between the hot and cold temperatures at each end of the exchanger. Once we have calculated the LMTD, we can find the total heat transfer rate. The heat transfer rate Q is simply U times A times the LMTD. This powerful method allows us to analyze heat exchanger performance by converting a variable temperature difference into a single representative average value. Let's apply the LMTD method to a real-world problem. Consider a heat exchanger being used to cool 3 kilograms per second of hot oil from 120 to 80 degrees Celsius. The oil has a specific heat capacity of 2,200 joules per kilogram per Celsius. To do this, a stream of water with a mass flow rate of 2 kilograms per second entering at 25 degrees Celsius is used. We know the overall heat transfer coefficient U is 200 watts per square meter per Kelvin. Our goal is to find the required surface area of the heat exchanger, A. The first step in any heat exchanger problem is to calculate the total heat transfer rate, Q sub U. Since we have both inlet and outlet temperatures for the hot oil, we can use the equation Q equals the mass flow rate of the hot oil, times its specific heat, times its temperature drop. Plugging in the numbers, we get Q equals 3 times 2,200 times the quantity 120 minus 80. This gives us a total heat transfer rate of 264,000 watts, or 264 kilowatts. Since all this heat flows into the cold water, we can use an energy balance on the water side to find its outlet temperature. We know Q is 264,000. This must equal the water's mass flow rate times its specific heat times its temperature rise, T sub C out minus 25. Solving this equation gives us a cold water outlet temperature of approximately 56.6 degrees Celsius. Now we have all 4 terminal temperatures and can proceed to calculate the LMTD. Let's assume a counterflow arrangement, as it's typically more efficient. For counterflow, delta T1 is the difference between the hot inlet and cold outlet temperatures. That's 120 minus 56.6, which is 63.4 degrees. Delta T2 is the hot outlet minus the cold inlet. That's 80 minus 25, which is 55 degrees. Plugging these into the LMTD formula gives us an LMTD of 59.0 degrees Celsius. The final step is to use the fundamental heat exchanger equation to solve for the area, A. We know Q equals U times A times LMTD. Rearranging for A gives A equals Q divided by U times LMTD. Plugging in our values, 264,000 divided by the product of 259.0. This gives a required heat transfer area of 22.37 square meters. This example shows the complete step-by-step process of designing a heat exchanger for a specific duty, from calculating Q to sizing the area A using the LMTD method. The log mean temperature difference, or LMTD method, is a powerful and widely used tool, but it has one significant limitation. It requires that you know or can calculate all four terminal temperatures of the heat exchanger. However, in many real-world design problems, you don't know all four temperatures. For example, you might have to select a heat exchanger to cool a fluid from a specified inlet temperature to an unknown outlet temperature, using a cooling fluid with known inlet and flow rate. For these cases, the LMTD method is an iterative process which can be cumbersome. A more convenient approach is the effectiveness NTU method. The effectiveness NTU method uses two dimensionless parameters to analyze heat exchangers without needing to know all four temperatures. The first is effectiveness, epsilon. Effectiveness is defined as the actual heat transfer rate achieved by the exchanger, divided by the maximum possible heat transfer rate. The maximum possible rate would be achieved by an ideal, infinitely long exchanger in counterflow. The actual heat transfer rate can be calculated for either fluid. The maximum possible rate, Qmax, is always the heat capacity rate of the fluid with the minimum capacity, C sub min, multiplied by the maximum possible temperature difference. This means effectiveness is a dimensionless number between 0 and 1. It tells you how close the real heat exchanger comes to the ideal performance. The second parameter is the number of transfer units, or NTU. NTU is also a dimensionless number and represents the size of the heat exchanger. It's the product of the overall heat transfer coefficient and the area, divided by the minimum heat capacity rate. NTU can be seen as a ratio of the thermal conductance of the heat exchanger to the thermal capacity of the fluid with the smaller capacity. The beauty of the effectiveness NTU method is that the effectiveness, epsilon, can be expressed as a function of NTU and another parameter C sub ratio. This C ratio is simply the minimum heat capacity rate divided by the maximum heat capacity rate. The exact functional relationship, F, depends on the type of heat exchanger, parallel flow, counterflow, shell and tube, etc. These relationships are typically presented as charts or simple equations. The effectiveness NTU method is particularly well suited for situations where you need to predict the performance, outlet temperatures, of an existing or specified heat exchanger. Let's demonstrate how to use the effectiveness NTU method with a practical example. Consider the same heat exchanger from our previous LMTD example, but this time, let's say we're given the area A and the inlet conditions, and we need to predict the performance. Let's find the outlet temperatures. We have the hot oil inlet at 120 and cold water inlet at 20. The overall heat transfer coefficient is 200, and the area is 22.37 square meters. Our goal is to find the two unknown outlet temperatures, T sub H out and T sub C out. First, we calculate the heat capacity rates for both fluids. For the hot oil, the capacity is 3 times 2200, which is 6600. For the cold water, it's 2 times 480, which is 8360. Comparing these, we see that the hot oil has the minimum heat capacity rate, so C sub min is 6600. Next, we calculate the NTU and the C ratio. NTU is U times A divided by C sub min. That's 200 times 22.37 divided by 6600. This gives an NTU of approximately 0.678. The C ratio is C sub min divided by C sub max, which is 6600 over 8360. This is approximately 0.789. Now we can use the formula for effectiveness for a counterflow heat exchanger. The equation is quite complex, but plugging in our NTU and C ratio values gives us an effectiveness of approximately 0.4. An effectiveness of 0.44 means the heat exchanger is achieving 44% of the maximum possible heat transfer. Finally, we use this effectiveness to find the heat transfer rate Q. Q equals epsilon times C sub min times the temperature difference between the hot and cold inlets. That's 0.44 times 16600 times 95, which is 276,460 watts. This matches our previous LMTD calculation, allowing for rounding. Now we have Q and can solve for the outlet temperatures using simple energy balances, just like we did with the LMTD method. This example illustrates how the effectiveness NTU method provides a powerful, non-iterative way to analyze heat exchangers when you know the geometry, A, but not all the outlet temperatures. We have covered a significant amount of material on heat transfer and heat exchangers. Let's summarize the key concepts we've explored. We began with the fundamentals, the three modes of heat transfer: conduction through direct contact, convection through fluid motion, and radiation through electromagnetic waves. We learned how to model these modes using Fourier's law, Newton's law of cooling, and the Stefan Boltzmann law, and how to combine them into powerful thermal resistance networks. We then shifted our focus to heat exchangers. We saw how to consolidate all resistances into a single overall heat transfer coefficient, U. We also discussed the critical impact of fouling on U. We explored how to find the convection coefficients using dimensionless parameters and empirical correlations. Finally, we analyzed two key methods for predicting heat exchanger performance: the LMTD method, ideal for design when all four temperatures are known, and the effectiveness NTU method, perfect for performance analysis when only inlet temperatures are known. Mastering these concepts will provide you with a robust framework for understanding, designing, and troubleshooting heat transfer systems in a wide variety of engineering applications. Thank you for your attention. Thank you for watching. If you found this video helpful, please subscribe to ThetaWise for more in-depth engineering content. See you in the next lesson.